As you all know, the sun is the ultimate origin of wind. In this video, you'll see how heating of the Earth's surface leads to wind and which patterns the wind will consequently follow. Wind is created through temperature differences on the Earth's surface. Here you see a map of the mean surface temperature in January. Obviously, the temperatures are higher around the equator than around the poles, and this is driving the global patterns of wind. If you look at the Earth's atmosphere from the side, you can see how the temperature variation over the Earth's surface leads to circulation cells. Around the equator, warm air rises, and higher up in the atmosphere, this air has to make place for new rising air, and therefore it moves either north or south. Eventually, it will hit colder air coming from the direction of the poles. At this point, the two airflows sink back to the Earth's surface. A similar but opposing circulation can be seen at the poles. Cold air at the North Pole sinks and has to move to the south. There it encounters air coming from the south, and these two flows have to rise. Because of the thickness of the atmosphere, there is room for 3 of those cells between the equator and each pole. At points where the air rises, it leads to a low pressure region in the lower atmosphere. Where the air sinks, the lower atmosphere becomes a high pressure region. Because of the size of the circulation cells, the northwest of Europe typically experiences low pressure regions. This typical latitude of high and low pressure regions is visible on this map of a particular day. The high pressure region is around the Mediterranean, and the low pressure region is around Scandinavia. The white lines represent isobars, or lines of equal pressure. The wind moves along those lines. In first instance, you would actually expect the winds to go directly from high pressure regions to low pressure regions, but we'll see later how the Earth's rotation causes the wind to deviate from this direct route and follow the isobars. Because the low pressure regions are in the north and the high pressure regions are in the south, we'll see that this causes patterns with mainly westerly winds in northwest Europe. Let's have a look at this rotating disk and a ball that is moving along a straight line in a fixed frame of reference. If we would look at the motion of this ball from a frame of reference that is fixed to the disk, it would appear to be curved to the right. You can see this in the lower part of the image. The same happens if we would have wind moving in a straight line from the North Pole to the equator. Looking at the Earth from the top, so at the North Pole, the Earth's rotation is counterclockwise. While the wind is moving from the pole to the equator, the Earth underneath it therefore moves to the right. Looking at the wind from a frame of reference fixed to the Earth, the wind would then appear to curve to the right. The fictitious force that causes this curvature is called the Coriolis force. If we were to look at the Coriolis force in more detail, we would find the law of Buys-Ballot. This law states that on the northern hemisphere, wind turns clockwise around high pressure regions and counterclockwise around low pressure regions. This explains our pattern of westerly winds in northwest Europe. The upper two circles show the patterns of wind around high and low pressure regions on the northern hemisphere. Imagine the low pressure region on the right to be north of the high pressure region. The wind will then move from left to right between the two pressure regions, so in westerly direction. So far, we have looked at the global patterns in temperature variation over the Earth's surface, leading to large patterns in the wind. Now we're going to look at some local temperature differences leading to local patterns in the wind. If we have a coastal region with land on one side and sea on the other side, we also get temperature differences. During the day, the land heats up faster than the ocean, which has quite a constant temperature during the season. This means that the air rises over land, leading to a low pressure region, and it drops over sea, leading to a high pressure region. This causes a sea breeze coming from the sea to the land. At night, the Earth's surface cools down, while the sea keeps the same temperature, and we get a reversal in the pattern. You can recognize this pattern in the Netherlands. The sea breeze increases the predominantly westerly wind during the day, and at night the wind drops due to the reversed flow. A similar effect can be found in mountainous regions. In principle, the higher you go, the colder it becomes. However, during the day, the surface of the mountain peaks will heat up faster than the surface of the valleys. This causes air to rise against the mountain slopes and to drop in the valleys. At night, the mountain slopes will cool down quicker than the valleys, and also here the pattern reverses. With this last example of local creation of wind from solar energy, we will close off this overview of the origin of wind.